Okay, so today what for this part, what I would like to talk about is a is sort of an application of the various techniques that we've discussed to on some research problems where the results are actually from the final results are from the past couple of years. So this is on estimating the number of edges in a graph. Okay, so the first results in this form are by Feige in 2008. There was a follow-up by Kohlreich and Ron in 2009, and then more recently, Eden, Ron, and myself in about 2017 gave simplified proofs for this main result. So, and since then, there's actually been some more recent work on this problem. So, let me tell you what the question is. And a lot of its motivation in recent times has been on social network analysis. Given query access to a graph, so we'll think of the graph as just simple and undirected. Determine the number of edges. Number of edges in G. So I'll say the number of vertices is n, this is m, the usual, and I'm going to think of, obviously I can write m as the summation of dv divided by 2 times n, where dv is the degree of vertex v. So this is number of edges or average degree. I'll say n is known. So you know the number of vertices in the graph. Ideally, you want to determine the number of edges without reading the whole graph. So estimate m without seeing the whole graph. So this is really a sublinear algorithm. So I should now then say that what you want here is a sublinear algorithm. And it's sublinear because it's less than linear. So without seeing the whole graph. So what can you actually do? So you have 3 kinds of query accesses to the graph. The first is the random vertex query. The random vertex query is get a uniform at random vertex. So you can get, by the way, the fact that n is known is only required to determine m. If you want to get the average degree, you don't even need to know n. So we can, phrase this problem in 2 different ways. In many social network contexts, it's actually the average degree that often people will care about. So they'll say, I want to know the average degree of Facebook. And of course, this is skewed, or let's say in Twitter, right? You want to know the average degree, and this is skewed by some high degree vertices, and I want to determine the entire average, even though it's skewed by a few individuals. So the second is the degree query. Let's say get the value of the degree of a vertex. So what Feige analyzed was just this. So it's really simple. You can get a uniform random vertex, you can query the degree, and you want to know how good an estimate can you get to the average degree of a graph. And I'm going to add this in, and we'll talk about this either at the end of this lecture or the next lecture. I'll say a random neighbor query is given v, get a uniform at random neighbor of v. But I want to start by just doing the first 2. And so the question actually becomes a really fundamental question. So let me set some notation over here. So I'm going to use d bar to be the average degree, which is simply the sum of d of v divided by n, right? The sum over all vertices, and this is also the same as 2 times m divided by n. Okay, so given uniform at random k vertices, or I should say given k uniform at random sort of independent vertices v1 to vk independent, how good is the estimated degree? So I'll say d of vi, I less than k divided by k. How good is this as an estimate of this, of the average degree? Now, in general, okay, so in general this seems sort of hopeless, because if d of 1, d of 2, d of n, right? This is what I will call the degree sequence. If this is an arbitrary sequence of numbers, of let's say of positive integers, this problem is hopeless. And you all know from basic statistics that to get the average of a sequence of numbers, if the numbers are arbitrary, there's really no hope. And moreover, let's just say that all the numbers are strictly positive. So let's assume that for all v, the degree of v is strictly greater than 0. So we're just saying there are no isolated vertices. Which kind of makes sense, right? Because if you have lots of things that are just isolated, then your graph is probably not interesting. And in any case, one can in general deal with this. One can remove this assumption and then have some dependence on the number of isolated vertices. But my point is, if this sequence of degrees is an arbitrary sequence of integers, then positive integers, you're hopeless. But let's walk through some math towards this. Yeah, just to sort of make this more formal. Like, how hopeless is it going to be? Okay, so let x be a random variable where x is equal to the degree of v, where v is uniform at random from v. So the expectation of x is precisely the average degree. So what is the variance of x? Well, this is the expectation of x squared minus the average degree squared. And if you kind of crank out the expression over here, so what is this? This is simply saying it's a summation of all vertices of the squared degree divided by n minus d prime squared, right? Because this is the expectation of the squared. So let's do Chebyshev and just see what we get. So this is a calculation that we have seen multiple times in the course, but let me just repeat it. So by Chebyshev, how many samples needed for, let's say, for a 1 plus epsilon approximation, or even I could even say for an O of 1 approximation, just to get anything. Well, let's take t samples. And let's look at y being the summation of xi, I less than t. So xi is independent copy of X, right? So this is an independent copy of X. So the expectation of Y is T times the expectation of X. That's just linearity of expectation. The variance of Y is equal to T times the variance of X, and that's because that's by independence. That is because of independence. So the standard deviation is square root T times the standard deviation of X. I'm just sort of walking through the Chebyshev calculation again. And so for Chebyshev, we need that to get anything useful. So for Chebyshev on the random variable Y, you need that the standard deviation of Y should be much smaller than the expectation of Y, right? I mean, that's when you'll get anything. And so what you get is, if you plug this in, I mean, and again, we've seen this calculation over and over again, but let me do it again. And this is just the standard deviation. The expectation is T times expectation of X. And so what we need is for T to be at least essentially sigma X squared divided by the expectation squared, which is again just the variance of X divided by the expectation of X squared. And remember that the expectation is just the average degree squared. So, I spent 5 minutes essentially just reworking something that is fairly straightforward, which is simply to say that if you have a given variance and a given expectation, then how many samples do you need to get any sort of convergence by Chebyshev? Okay, this is sort of your quick back of the envelope. So let me now plug some values in over here. So what is the variance of X? And we discussed this. This was summation over V dV squared minus d bar squared. This is d bar squared, and this will give you 1 over n summation of dv squared divided by d bar squared minus 1. And so you're trying to understand what is the sum of squares of degrees with respect to this. Now, what is the worst case for this? Suppose you fix the average degree. What is the worst case for the sum of squares? So I'll say given sequence of numbers with a fixed average, how to maximize the sum of squares? Or what is the maximum? Does this question make sense? Or I should maybe say, what is the maximum? What is the maximum? How do you maximize it? So I give you a bunch of numbers, right? So you have these numbers d1 up to dn. What should you choose these numbers to be to maximize the variance? Put everything on one number, right? Basically, try to maximize an individual entry. So, suppose d1 is equal to d, or I should say maybe d1, the first one, I'll make that the maximum. I could make that being n minus 1, and d2 equal to d3, and so on and so forth, equal to dn is equal to 1. What is the graph? What is this? Can you give me a graph that has this degree behavior? A star. Right? So you have a star. The degree in the middle is n minus 1. All of these degrees are 1. the average degree is basically 2 minus little o of 1. I mean, the little o of 1 is it goes to 0 as n goes to infinity. What is the summation of dv squared? Up to thetas. What is the sum of squares? Give me up to theta. Theta of n squared. Go and plug this back in over here. Right? So this was what we want t to be. And you'll see that this is basically omega of n, which kind of makes sense. The average degree is 2, but with little o of n samples, we do not see the center. So what is the empirical average with few samples? What is the average that you're going to see if you just took little o of n samples? What do you see? It's fairly 1, right? The empirical average is 1. Because all you see are these endpoints. You'll never see the center, but the average degree is 2. So the variance is unbounded. Variance is the worst possible, actually. So seems hopeless. Except what Feige observed is, even in this bad example, you are only off by a factor of 2. Right? So seems hopeless for a 1 plus epsilon approximation. Suppose we are okay with a constant factor approximation. Can we deal with the unbounded or this unbounded variance? It seems that if you try to plug Chebyshev in, you won't get anything. Because for Chebyshev to kick in, you need t to be at least this much. So the variance is unbounded. So a naive application of Chebyshev won't work. So this is actually a much more fundamental problem if you think about it, is that how can we deal with an unbounded variance? Because it seems like the first thing you do is Chebyshev. Can we beat what we get from Chebyshev? And indeed what Feige showed was that this is possible. So what Feige proved, and indeed what I'm going to present is not Feige's proof, but rather a simplified version of the proof that was given by Ed and Ron and myself. And what they now I'm gonna sort of ignore dependences on epsilon, and I'm just going to write this as in O of root n divided by epsilon cube. By ignore, I mean I'm not going to optimize. You can actually get something better than epsilon cubed, but let me just put epsilon cubed for the theorem statement. So root n samples suffice to get a 2 plus epsilon approximation for the average degree. What this means is that what we'll output is the probability that the estimate is, and you'll see that it's fairly specific. It's going to be of this one. The probability that the estimate is not in this, which is the average degree divided by 2 times 1 minus epsilon, and the average degree times 1 plus epsilon. So the probability that your estimate is not in this is going to be less than 1/3. Okay, so this is the guarantee that I'm going to show you. And you might say, but why is it a 2? Well, you cannot beat a two-factor approximation in this model. As the star shows. Right? And the star kind of clearly shows that you cannot beat a two-factor because you're only going to sample the periphery. You're only going to sample the leaves if you sample lit low of n samples, and so you're not going to hit the center, in which case you're going to be off by a factor of 2. Okay? So any questions about what the statement of the result is? Any questions? Okay. So now as we said, the problem, or I should say the challenge, is we cannot use Chebyshev, or frankly, or any concentration directly on the random variable x. And so the solution, and which is, it's a non-trivial solution, will be to carefully remove outliers. So let me now sort of explain this in more detail. It's convenient. Let us sort in descending order, in I'll say non-increasing order. So I'll just say that d1 is greater than equal to d2 is greater than equal to, I'll use subscripts over here, where di is the ith largest degree. Right? And so we assumed no isolate, so this is all strictly greater than 0. And as we discussed, the problem is when a few large entries dominate the sum. And so towards that, you can actually apply the following lemma. So I'll just say that for all k and n, the summation of the top k degrees is at most the summation of the remaining degrees plus k choose 2. Okay, I'm just saying the sum, and this is where we use the fact that the di's are degrees. Remember, we said if the degrees were actually degrees of an undirected graph, undirected simple graph. Okay. Can anyone hazard a guess as to how you'd prove this? The proof is actually not very complicated. I'm not going to give a full proof, but what I will do is give a sketch, and the scribe can fill in the details. So let's look at the top k degrees. So how many vertices are here? There are k vertices here. K vertices. Right? And so each of these has got these many things, these many edges going out, or going out of the vertex. These edges have a second endpoint Now this second endpoint either has to be within the set or it has to be over there. Right, this endpoint is either going to lie in here or it's going to lie in there. But how many edges can be contained in here? How many edges can be contained in here? At most k choose 2. So all the remaining edges have to land in here. But any edge that lands in here contributes to this sum. Any edge that lands in here contributes to this sum. There are at most k choose 2 edges that could actually land in here. That could be completely contained in here. Does that make sense overall as a proof sketch? Questions? Sure. So I want to prove that the sum of the top k degrees is at most the sum of the remaining degrees plus k choose 2. So what I'm going to do is I'm going to take my graph, I'm going to split it into two parts. Here are the vertices. Yeah, the vertices of the top k degrees. The remaining vertices, or I split the vertices. Now I say that summation, the left hand side is the number of edges that have one endpoint in here, at least one endpoint in here. At most k choose 2 edges can have both endpoints in here. So all the remaining edges, that is the summation of di minus k choose 2. So if you look at this, this is the number of edges whose endpoint must lie in here. Right? And that's the proof. So I will mention at this point that this is actually the easy converse of a more famous theorem, and this is known as the Irish Gal I Theorem, that states for any integer sequence d1 greater than or equal to d2 to dn strictly greater than 0, if this is the converse of the theorem, if this holds, then there is a graph whose degrees are d1 to dn. This is the converse. This is a much harder statement. There's actually a simpler proof that was given by Haval and Hakimi that shows this. So it basically says, remarkably, this condition actually characterizes sequences of degrees. Okay, this is the Irish Gal I theorem, but we don't need to apply or prove the Irish Gal I theorem. We only need the easy converse, and the converse is simply that if d1 to dn are degree sequences, then this condition holds. Okay, so now let's go back to this lemma that we have now. So this lemma is very useful because this lemma tells us that the sum of the top entries is less than equal to the sum of the remaining entries. So think of this is what's going to kick up your variance. But the part that kicks up your variance is at most the sum of the remaining plus this additional annoying term. Okay, so let's go back to this statement. Remember, so we need to estimate. We need to estimate the summation of di. Over all I less than n divided by n. This is what we need to estimate. So I can write this as the summation of the top part plus the summation of the remaining part. Okay. Now, by our lemma, I can write this as 2 times the summation of di I going to k plus n plus k choose 2. So I simply replace this part by the lemma. So this is by the lemma. Okay. So I can write my average degree, which is what I wanted, is at most twice the average of the smaller values. And obviously, right? Obviously, this is going to be at least that. Right? This is sort of obvious because I'm just dropping out all of these terms. So this quantity here, which is the average of all degrees, is at least the average of the smaller degrees. Does this make sense? And note that you basically have the same quantity here. Here's your factor of 2. Okay, questions? Okay. So now, of course, we still haven't come to how we're going to do the analysis, but let's go back to this and say that we will try to estimate the summation of di I going greater than for carefully chosen k. Because if we can estimate this accurately, if we can estimate this quantity accurately, then that quantity gives a 2-factor approximation to the average degree with an additional error, which we need to control. And the error is going to sort of determine our choice of k. Obviously, the smaller you make k, the smaller your error is, which is sort of obvious. If k was 0, then there would have been no error. If k is n, then you get a lot of error. Sorry, this should be divided by n over there. Okay. All right. So now let's just do a back of the envelope calculation. Think of d is sort of like theta of 1. It's a sparse graph. What should k be? What should you choose k so that this error is sufficiently small? What should you choose k to be? Square root of n. Because if you choose k to be square root of n, then square root of n squared, which would be n divided by n, this would be O of 1. And then by choosing some epsilons, we can make it smaller than the average degree. So specifically, let's set k to be equal to the square root of epsilon n times the average degree. Okay? And let's go back and plug this in over there. So this is now going to be my value of k. What I get then is that the summation of ik di divided by n, so at most the average degree, times 2 summation of di I going strictly greater than k divided by n plus, okay, so up to some little of 1 error, because I'm going to just replace, so well, I can write it in the following way. So essentially what I get over here is k times k minus 1 divided by 2n, and this I'm going to write basically as epsilon nd divided by 2n. I get that. And so what I get is that d prime is at most 2 times the sum of the larger parts divided by n. So this is the average of the larger part plus epsilon d. So I'm being loose with the constants here. So I get an epsilon by 2, but I'm just being loose with the constants. Does this make sense? So if I chose k to be sort of this magic parameter, then the error is going to be small. Of course, you might say, we don't know what d prime is. How are we going to set any of these choices? And again, like all of this is like a thought experiment that is going to be part of the analysis. It is not going to actually appear in the algorithm itself. So this is my choice, and this is where the root n comes from, and this is where the 2 factor comes from. Okay. Any questions? Okay. Okay, so now with that, let me go back. Let's go back to what we were interested in initially, which is, we need to choose the number of trials. We need to look at that, or rather, we don't even, let's ignore the denominator. So we need to go back to the summation of xi. Remember that xi is an independent copy of x, where x is basically just equal to dv for a uniform at random v. Okay. So I realize that my use of I has been overloaded here. So let me actually use j for this. Okay. So j is going to refer to the trial, where I is sort of indexing over the vertices. So what I would like to do is to somehow ignore, so remember, what we're doing in our estimate is ignoring the top k entries. So let's look at the truncated random variable. So let me look at the truncated random variable, which is going to be xj prime. So I'll say xj prime is going to be equal to xj if the degree of v, that is the vertex that I get, is less than equal to the kth degree and is going to be 0 otherwise. Okay, so the expectation of xj prime is going to be precisely the summation of I greater than k. Well, it's going to be it's going to be at least this quantity. It's going to be technically at least this quantity. And obviously this is at most the average degree. And the reason I put at least and not strictly is because there could be degrees that are the same. So this expectation is pretty much exactly what we want here, which is so the truncated estimate is that. What is the maximum value that xj prime can take? What is the maximum value that xj prime can take? dk, right? So this is at most dk. So again, let me give you a sort of picture intuition for what is going on. So I'm going to draw the degrees as bars, right? So this is degree 1, to, so think of this as D1, D2, D3, so on and so forth, until we reach some dk, and then we have everything that's left. So what we're saying is that we can effectively ignore the contribution of all of these entries. So recall k was epsilon n root d. Okay? So we know that the maximum value that this random variable can take is dk. Can we upper bound dk? Can you upper bound dk? How many entries have value at least dk? K. So obviously the summation of di over all the vertices, and remember this is just n times the average. This is certainly greater than equal to the summation of I less than k of di, and all of these are at least dk, so this is k times dk. Therefore, what we get is that dk is at most n times the average degree divided by k. Plug this in over here. What you get is that. So dk can be upper bounded. So dk can be upper bounded. And now it turns out we're in business. We can essentially apply Chebyshev. So let's look at this truncated random variable xj prime. So we know that the expectation of xj prime is at least what we want divided by the average. It's between the average degree and a good estimate of the average degree. Okay, so let me just to make this more precise, let me plug in this bound over here. So we know that this is at least greater than equal to half minus epsilon. So the expectation of the truncated random variable is a half approximation of what we are looking for. Now we also have a bound on the maximum value that this random variable can take. And so once we have that, we are in good shape, because the variance of this, which we can just say is at most the expectation of xj prime squared, which is at most the maximum value of xj prime times the expectation itself. And this we can write out, because we know the expectation is at most the average degree. The maximum value we have just bounded over here. So we write that as, plug that in, times d prime. Okay, so we have a random variable whose expectation is well behaved and whose variance is sort of also well behaved. How many samples do we need? Let's go back to our Chebyshev calculation, which says the number of samples you need is essentially the variance divided by the expectation squared. So we go here and we say how many samples to estimate xj prime. Well, the number of samples, we need to get at least the variance. So let me put down the variance there, nd prime divided by epsilon times d prime divided by the expectation squared. Again, ignoring constants here, which I can reset later, is the expectation squared is that. And so what I get from this process is essentially the square root of n d prime divided by epsilon. Sorry, let me just sort of stop that 1 second. Sorry about that. So how many samples do we need to estimate xj prime? We need the variance divided by the expectation squared. We have a bound on the variance. That's the upper bound. And we have a bound on the expectation, which we know is basically just d bar. And so we get that the number of samples we need is basically n d bar divided by epsilon. Okay. Now, I'm not going to state this as I'm going to state this as a formal claim. I'm not going to give the proof. And scribe, please work out the proof. So I'll just say that let t be greater than or equal to some c times log 1 over delta divided by epsilon square n divided by epsilon d prime. Then the summation of xi prime, I should say xj prime, j less than t divided by t. So this is going to be a 1 plus minus epsilon approximation of the expectation of any one trial with probability at least 1 minus delta. And the proof is basically a Chernoff bound. It's a Chernoff bound on the random variables xj prime divided by the maximum value of nd prime divided by epsilon. And note that this is basically going to be between 0 and 1. Okay, so basically because you have an upper bound on the maximum, you can bound the variance, and indeed you can also apply the Chernoff bound. Okay, so what we have at this point is we know that the summation of xj divided by t is going to be at least the summation of xj prime divided by t, and this, with high probability is going to be at least, remember, let's go back to what we know. We know that the expectation is at least the average degree times a half minus the epsilon. You have to crank out a bit of the algebra here, but you will get is that this is at least the average degree times 1 minus epsilon. Okay, so what I'll do is I'll pause here, take any questions about this, because this was the major part of the analysis, and then I can talk about the rest of it. So just want to reiterate that I had a typo over here. So the number of samples again was the variance, that is this quantity here, divided by the expectation squared, right? And so what you have here is the square is going to contribute a d prime dependence in the denominator. So what this means is, because we know the average degree is at least 1, basically root n by epsilon samples suffice. And again, like in this theorem, we could simply assume that d prime is greater than 1, and we would be at least this bound here. So what this does, this analysis so far does, is it has dealt with the lower tail. So with probability at least 1 minus delta, this is the lower tail. The upper tail, well, let me just give you a trivial solution, and you can actually do things that are more clever than this if you want to optimize the dependence on epsilon. But the trivial solution is just to use Markov. And so what you could simply say is the probability that xj divided by t, the probability that this is more than 1 plus epsilon times the expectation or potential expectation is just at most this, which is less than 1 minus epsilon over 2. This is a very weak upper tail bound. It just says that with some tiny probability, which is just epsilon over 2, the answer will be accurate. So let me just sort of write this down together. And the claim, or maybe it should be more of a lemma, is to, if t is at least c log 1 over epsilon divided by epsilon square root n by epsilon, then the following hold. With, remember I set delta. I'm going to set delta here to be epsilon squared. So what you get is with probability at least 1 minus epsilon squared, the estimate that I get is at least 1 minus epsilon times the average degree divided by 2. With probability at least epsilon, this is really small, the estimate is at most 1 plus epsilon times d. So this is a strong upper tail, but it's a weak lower tail. Do you see how to remedy this? So think of this as a black box. I can get an estimate which is at least my desired value with very high probability, but it's at most my desired value with fairly low probability. So there's like a nice hacky fix to this.
Just combine the two bounds.
No, well, I mean, how do you combine the two bounds? So think of it as,
You just choose a number of samples. Like, we're going to choose 1 over delta. We're going to choose 1 over epsilon. And just add delta.
even if you increase the value of delta, you only change the upper tail. The lower tail is just Markov, which is independent of delta.
Yeah, but isn't the previous analysis giving us a better lower tail than this Markov lower tail?
The previous analysis only gives you a lower tail bound on xj prime, on the truncated random variables. The problem is that
the xj are bigger than the xj prime.
right, so it goes in one direction, which is why you get an upper tail bound.
I don't really understand.
So my point is, what this analysis tells you is that, okay, so let's go back to this. So remember, we have these sort of the sum of xj's, and we said the sum of xj's is at least the sum of x. I mean, I think I've sorry, my apologies. I've actually mixed the okay, so this is mixed up. So, well, okay, so no, it's fine. So the summation of xj is at least the summation of xj prime. Right, this is what we've shown. This concentrates well. So let's just draw a picture here. This is the summation of xj. We know that this is a summation of xj prime. So we know that this is going to be sort of this is going to be at least d over 2. But this could be really far out over here. We just know that this is a lower bound. Does this make sense? So summation of xj, let's say this is d over 2 and this is d bar. So we know that summation of xj prime is going to be in the desired range. Summation of xj is only greater than xj prime, but it could deviate in this direction. It's not going to deviate in this direction. So we know that it's guaranteed to sort of lie on this side, but we don't know whether it's going to lie on this part. We only have a very weak bound. The probability is only epsilon of being less than this.
Oh, I see. Yeah, sure.
So you only get one side. So the way to think of this picture here is like this is sort of the region where you want the random variable to be. The truncated random variable lies in the desired region. But the truncation in some sense depends on the average degree, which we don't know. How do we deal with this random variable? Well, all we can say is we have Markov, which just says that with at least probability epsilon it's going to lie in here, or it's going to lie below this point. So you have a small probability of lying below this, but you have a high probability of lying above this. Does that make sense? These are asymmetric bounds. So what's the fix? Because this is something you can boost easily, this you cannot boost. You could. I mean, you could do something mathematical and try to understand this. But if you didn't care about basically constant factor dependencies, there's an easy fix to this, which is, so you have this black box. Repeat this a bunch of times and take the minimum estimate. Okay, so let me write this down. So let me keep this black box over here, and let me just say that what you can do is repeat the estimate O of 1 over epsilon times independently, output the minimum amongst them. Do you see that if you did at least 1 over epsilon trials, one of them is guaranteed to be in this range, and all of the estimates are actually guaranteed to be above this because the upper tail is so strong? I mean, my apologies, because the lower tail is so strong. Because the lower tail is so strong. The lower tail bound is very strong. So you're guaranteed to be above the desired value with very high probability. So even if you did many trials, all the trials will be above this. And one trial is guaranteed to be at most this bound here. So with high probability, the minimum is going to lie in here. So this is like a quick trick to boost. So let me write down the guarantee. So if you repeat the estimate 1 over epsilon times independently, two things will hold. So you can argue that with probability at least 2/3, all estimates are at least d bar over 2 times 1 minus epsilon, and this is just union bound on the lower tail, which you can afford to do. But the second is at least one estimate is at most this quantity. Do you see why this is true? Let me sort of show this claim over here, right? You see why this is true? If you repeat this O of 1 over epsilon times independently, well, at least once this event is going to happen. Okay? This is an exercise. Okay? So I think I will end here. What I was planning on doing was also talking about the fact, so let me sort of lead on to what I will talk about next lecture, that if you actually have random neighbor queries, then you can improve the analysis and you can actually get a 1 plus epsilon approximation, not just a 2 plus epsilon approximation. And the ideas are very similar. The analysis is very similar. You just need to change the estimate carefully. You change the estimator, the random variable, carefully. But if you just have random vertex queries and degree queries, you get a 2 plus epsilon approximation using this mechanism. Again, this is sort of a quick and dirty proof. If you did not care about the dependence on epsilon, then this works. If you did care about the dependence on epsilon, then there are ways to improve it, and you need to do a much tighter analysis. Although I don't think that I have seen sort of the optimal analysis for this as of yet. So I think there is an open problem as to sort of what is the best dependence on epsilon you can get. So I will end here and take any questions.